ME347, Example 14. A pitot tube is used to measure velocity in a supersonic wind tunnel. A normal shock occurs in front of the tube that measures a stagnation pressure of 80 kilopascals after the shock. Before the shock, the temperature is at 160 Kelvin and a pressure of 10 kilopascals. Calculate the airspeed A before the shock and B after the shock. For this problem, we will assume steady, uniform flow of an ideal gas with constant specific heats in a supersonic wind tunnel. Note that because there is a normal shock, we know that the wind tunnel must be operating at a supersonic velocity above Mach 1 for the shock to appear. Also, we will assume the flow is isentropic before and after the normal shock that exists just in front of the pitot tube. Before we begin our analysis, let's look at a schematic diagram for the problem along with the corresponding temperature entropy diagram. For the schematic, the flow, which starts out supersonic, is moving from left to right. The static conditions just before the shock are indicated by the subscript X. After the shock, the static conditions are indicated by the subscript Y. A part of the flow then comes to rest at stagnation conditions at the tip of the pitot tube. Thus, the process on the temperature entropy diagram goes from the states labeled X, then Y, and then tip. Note that because this is an adiabatic process, even for the shock, the stagnation temperature and critical temperature at Mach 1 are both constant. Also note that because the process is assumed isentropic before and after the shock, these conditions all lie along vertical lines. For the normal shock itself, the entropy must increase and the shock must jump, which is indicated by a dashed line, from supersonic to subsonic flow. This means that at state X, the temperature is below the critical temperature, and then at state Y, it is above the critical temperature. For part A, calculate the velocity at state X before the shock. To do this, we will first calculate the Mach number at state X. To get started, we consider which relations we can use to go from our given pressures to the unknown Mach number. First, before the shock, we can use the isentropic stagnation relations for an equation for stagnation to static pressure ratio. Second, across the shock, we can use the normal shock relations for an equation for a ratio of stagnation pressures across the shock. This gives us two equations with two unknowns, which are the desired Mach number and the stagnation pressure at state X. Since we do not need to calculate the stagnation pressure at state X, we combine these equations to eliminate it and get a useful equation for calculating Mach number from pitot tube measurements called the Rayleigh-Pitot tube formula. From the given information, we know that the ratio of the stagnation pressure after the shock, measured with the pitot tube, to the static pressure upstream in the wind tunnel, measured with a static pressure tap that is usually in the wall normal to the flow, is 8.00. Note that the Rayleigh-Pitot tube formula cannot be solved directly to get the Mach number that corresponds to this pressure ratio. 4 options for obtaining a solution are available as links on my ME347 Canvas webpage. The first one is to read the values off of the compressible flow figures handout or using the figures in your textbook. The second option is to use an online compressible aerodynamics calculator. Third, you can download the PC compressible flow calculator, or fourth, you can download the compressible flow toolbox for MATLAB from NASA. First, we will use the normal shock flow figure for an ideal gas with a specific heat ratio of 1.4 available from the compressible flow figures handout. For our known pressure ratio from the legend, we see that it corresponds to the blue dashed dot line and the scale on the right. Starting at a value of 8 and reading across horizontally, we then go down to the x-axis to get the Mach number before the shock of about 2.4. Next, Looking ahead to Part B, we read that the Mach number after the shock is about 0.52, given by the black line in the scale on the left, and the temperature ratio across the shock is at about 2.1, given by the pink line in the scale on the right. Alternatively, we can use the compressible aerodynamics calculator. For this case, we go to the normal shock relation section and make sure the specific heat ratio is 1.4. Then we select P1 over P02 from the input pull-down menu, where the calculator is using 1 and 2 instead of X and Y for before and after the shock, respectively. Then input 10 divided by 80 in the window and click the Calculate button to evaluate the ratio, display the Mach numbers, and display all the property ratios. Again, we note that the Mach number before the shock is 2.417, the Mach number after the shock is 0.5214, and the temperature ratio is 2.056. From the known temperature upstream of 160 Kelvin at state X, we calculate that the temperature at state Y is 329 Kelvin. Next, we calculate the speed of sound for an ideal gas at this temperature to be 253 meters per second, and the velocity before the shock to be 613 meters per second. For Part B, we calculate the speed of sound after the shock to be 363 meters per second at the much higher temperature, and the velocity to be at a much lower value of 190 meters per second.